Imagine a world where digital systems don't just see the world in flat images, but in full three-dimensional space. This is the era of the point cloud, a collection of millions of tiny points that redefine how machines perceive our environment. From industrial robotics navigating complex factory floors, to autonomous vehicles perceiving their surroundings for safer navigation, point clouds are the backbone of next-gen spatial intelligence and extended reality. They power digital twins and telepresence, bridging the physical and virtual worlds. But capturing this level of detail comes at a massive cost, staggering data volume. A single scene can comprise millions of points, requiring gigabits of data every second. Transmitting this data wirelessly introduces significant challenges due to spectrum congestion. This is why 5G isn't enough. To make real-time 3D a reality, we must look toward 6G. Wireless spectrum is a finite resource. Managing millions of points without delay is the ultimate hurdle. In applications like remote surgery or autonomous driving, every millisecond counts. We need seamless flow for real-time processing and critical decision-making. Targets are strict, under 20 milliseconds for safe navigation and less than 10 for immersive AR. 6G aims to bridge this gap, but it requires a total rethink of how we handle point cloud data. Traditional point cloud compression, or PCC, has served us well, but it has reached its limits. We have video-based methods for dense clouds and geometry-based methods for sparse ones. Video-based methods project 3D points into 2D images, leveraging existing video codecs. Geometry-based methods use octrees to map space directly, but they can be computationally heavy. Voxelization can introduce errors, sacrificing the fine details needed for precision modeling. Graph-based approaches utilize relationships between points, but they are difficult to scale for 6G. The complexity of these methods presents a bottleneck for real-time, resource-constrained environments. Deep learning is now enabling end-to-end frameworks that handle encoding and decoding seamlessly. We are seeing a paradigm shift, from minimizing bit errors to optimizing task performance. In the world of 6G, we focus on the meaning of the data, not just the individual bits. This is semantic communication, powered by Deep Joint Source Channel Coding, or DeepJSCC. It integrates source and channel coding, optimizing transmission beyond traditional metrics. The system extracts essential features, reducing the number of points while maintaining meaning. This approach provides incredible robustness against channel noise and interference. It eliminates the cliff effect, ensuring that even as signal drops, the 3D data remains usable. New hybrid strategies combine the best of both worlds, digital for structure, analog for detail. A digital skeleton of key points is transmitted first to provide the robust structural framework. Density analysis identifies these key points, ensuring the most critical data gets priority. Then an analog stream refines the scene, adding back the fine details and attributes with precision. This hybrid synergy addresses scalability, allowing 6G to handle point clouds of any size. We're also exploring representational compression, inspired by neural radiance fields, or NeRF. Instead of sending points, we parametrically encode the 3D relationships into neural network weights. The transmitter only needs to send these parameters, a fraction of the original data volume. The receiver then queries the network to regenerate the complete point cloud at any coordinate. This drastically reduces bandwidth while maintaining high data fidelity for the 6G era. In the future, sensors won't work in isolation. Multi-view acquisition is the new standard. Distributed sensors on vehicles and infrastructure will collaborate to build a complete 3D picture. This often results in overlapping data. Instead of wasting bandwidth, we can leverage this overlap. Using hypergraph-based coded transmission, we can optimize how this shared data is shared. It ensures every vehicle gets the data it needs to perceive what its own sensors cannot see. Coded combinations reduce the number of required transmissions by nearly half. This massive gain in efficiency makes real-time collaborative awareness a 6G reality. We are charting a path toward efficient, reliable, and low-latency wireless transmission, seamlessly integrating 3D spatial data into the interconnected fabric of our future. The future of wireless communication is 3D. Welcome to the era of the point cloud in the air.